Okay, well, we'll get started here. So project number 1 is due on Tuesday at the beginning of class, so please have it emailed to me by then. I did find one small typo in the project itself, so if you have a copy with you, please take it out. Just simply on page 2, there was a sentence in part H that should have been in part I. I don't know what happened there, so please make that change. And it will make sense what that sentence means by the end of today. Okay. Also, I want to mention about the videos that I record for every class. The last 3 videos, I've had a slight, there's a slight change in the format of the videos. I just in case you're wondering, I want to bring it to your attention. So if I click on one of the video links, eventually, after 10 seconds there, I will get to a video. There we go. So the first few days of class, I use a software package called Camtasia Studio, and that would just allow me to record everything on my computer. And then after class, I go back to my office and do about 10 minutes of stuff to the video, do some other post-processing, and eventually upload it to the server. This semester, UNL has finally got a nice, what's called lecture capture system called Camtasia Relay, made by same people making Camtasia Studio. It kind of automates the process for instructors. And so I've switched over to the Camtasia Relay, and it does all the post-processing itself. And there's 2 small things I want to point out with these particular videos. First of all, if you notice in the right-hand corner, you have the picture of me again. But it's a little transparent, and unfortunately, I cannot change that at all. I've asked the appropriate people on campus about if that can be changed, and they say no, it can't be. So just have to live with me being transparent there. Over here on the left-hand side, we no longer have the table of contents. I don't have a way that I can get a table of contents using this software, but the search, though, is enabled. And this actually is an audio. It searches the audio. So, for example, if I search for regression, it looks throughout all the audio that I've actually, the actual stuff that I say in class, and it looks for where I said the word regression. So in a sense, it's actually maybe even a little bit better than a table of contents. This search is not perfect. So, again, what it basically has to do is translate all my audio to text and then search the text. But it seems to do a pretty good job in the little bit that I've tested. So if I wanted to go to a particular place in the notes or in the lecture where I said regression, I go right there, and it automatically fast forwards me to that location. So nice useful tool. Any questions? Any questions about anything before we get going on here? Okay. We left off on page 222. So just to review a little bit here. Get my red pen out. So we can represent our population regression model 2 different ways. We can represent it as y is equal to beta 0 plus beta 1 times x plus epsilon, where epsilon is distributed independent normal 0 sigma squared. And also, if we took the expected value of that same equation, we get expected value of y is equal to beta 0 plus beta 1 times x. So what that second equation means is that given a particular x, on average, what would I expect the corresponding y to be? And I have this nice little equation that tells me what it would be. The first equation, though, says for a particular x, let's say maybe a particular person in your sample, what was their corresponding value of y? Now, the big difference then between the two equations is that basically this expected value of y is a constant. So, whenever you take an expected value of something, you just get like a constant back. The first equation, though, that y is a random variable. It's going to be a very important thing for today's lecture to understand the difference between those two elements. And last time what we did was we looked at how to find a confidence interval for the expected value of y. So for example, relating this to the high school and college GPA example, we could say something like we're 95% confident that what I would expect the college GPA would be for students with a high school GPA of, let's say, 3.0, what I would expect is between whatever this number is and whatever that number is. So again, what I would expect the average college GPA to be for any student who has a high school GPA of, let's say, 3.0. Now, essentially then what we're doing is this. If we look at in terms of this picture here, we pick a particular x, and we're trying to find a confidence interval for that part of the line with respect to the y-axis. And what we're hoping is that that confidence interval contains that part of the line at that x. Now today what we're going to be doing is to try to find out a confidence interval for y itself. So we want to be able to say with like 95% confidence that y is between two different numbers. So for example, let's say that there's a new, let's say we already have our regression model and a new student has applied to UNL, and we want to come up with a confidence interval for how we would expect they would do here at UNL in terms of their college GPA. That's where this kind of interval would be of interest rather than the previous interval that we looked at last time. And so what we're trying to do now with this interval that we're going to be learning about today is try to capture those green dots. We want for a particular, let's say, x, let's not pick that one. For a particular x, we want to construct an interval that contains that green dot. That's what we're hoping for. Now, which of these intervals, the one for the expected value of y or the one for y itself, which interval do you think will be wider?
Specific value.
What?
The expected value is the mean, so it should be closer to the trend line.
I guess that's one way to think about it. So the answer is the interval for y. And basically what you're saying is, well, for the other interval, expected value of y, we're looking at the middle, essentially, of all the points. Essentially, that's the idea. Remember what expected value of y is, though. It's a constant. Once you take the expected value of a random variable, it's a constant. Where now what we're trying to do is find an interval for a random variable. And we can see from the green dots and how they vary, there seems to be a lot more variability in the green dots than there is in just a single straight line. And thus, that is why we will have wider intervals for y than what we did for expected value y. And you will actually see that mathematically how that comes about. Now, before we proceed to take a look at the interval, there's two things I need to say first. So again, what we want is a confidence interval for y. Well, there's I guess, a particular set of terminology that has developed to try to help, I guess, students know the difference between confidence interval for y and confidence interval for the expected value of y. And that terminology is that the confidence interval for y, it's not actually called a confidence interval. Rather, what it's called is a prediction interval. It's a confidence interval. Trust me, it's a confidence interval. But people just tend to call it a prediction interval instead. Okay? So, to be consistent with the book and what, generally speaking, you will hear the terminology used outside this class, I will call it a prediction interval as well. Second, last time we looked at the book's notation, or we saw the book's notation, and basically for the particular y that we were interested in terms of the expected value, they always put a subscript h there to indicate, well, it could be particular, correspond to a particular x that's in our sample, or maybe not in our sample. But it's some corresponds to some x out there, x sub h. Well, then you get y sub h, or expected value y sub h. And we could, and you'll see this in other books too, we could just simply call then this y that we're interested in a prediction interval. Well, we could just call that y sub h as well. But our book goes one step further and instead says we're going to call this y sub h parentheses new. And the reason being is because you can kind of think of, the purpose of doing something like this is that let's say that you already have your model, and now you want to use this model for, let's say, a new person, like in the high school and college GPA example that we just looked at, a new person, and you want to find out what their college GPA should be. So since this is a new person, that's where that notation comes from. And I'll use their notation as well. Generally speaking, I try to keep using the book's notation so that when you're reading the book you don't get confused. But I will make small adjustments when I think it's really worthwhile to do. Okay, so let's talk about how we can find this prediction interval. You're going to see a lot of similarities to what we did last time for our confidence interval for the expected value of y. Last time, let me actually do a little split screen here so that we can go back and forth. See, there we go. So last time for a confidence interval for the expected value of y, that's in the top portion of the screen, we found a quantity that had the expected value of y in it that also had a t-distribution. And then through using some math, some algebra, we were able to get an interval then that just had expected value of y in the middle and everything else on the outside. Well, essentially we're going to do the same thing here. One can show that this quantity right here has a t-distribution with n minus 2 degrees of freedom. Notice the differences between the two, between what's in the top and what's in the bottom. In the top before we had y hat sub h minus expected value of y. You probably would want to use y hat to predict the expected value of y. Well, in this particular case, we have our quantity of interest, this yh new, minus, well, what we would use to estimate it. Again, you would expect y hat. Look what's in the denominator of the top portion of the screen. The square root of the estimated variance of y hat. Essentially, though, one could have also said, rewrote it like this, where I put the expected value of y in there as well. Why are those two different quantities equal to one another? Yeah, because the variance of an expected value is 0. So, what's the variance of the number 3? 0. It's 3. The number is 3. Oh, that's weird. I didn't mean for that to move down there, but we'll just erase this. So I'm using a tablet PC here, and there's one thing that they haven't quite worked out in the 9 years that, or actually guess now 10 years, that tablet PCs have existed. And that is, if you do a split screen and you write on different portions of the screen, it doesn't all work out. I'm looking forward to the new version of a tablet that Microsoft's supposed to come out with soon called, I think it's called Surface or something like that. Anyway, notice here in the denominator, we have essentially the same thing that we had as in the top part of the screen. Now we have the square root of the estimated variance of y hat h nu minus y hat h. And we'll look at how to actually calculate that shortly. But now that we have this quantity that has a t-distribution, then it just goes back to what you would learn in your very first stat course about, well, how do you form a confidence interval? Well, you have now this probability statement that you can make. Again, think of the stuff that's in the middle of that probability statement as a random variable. So this is a random variable, and it has a t-distribution. Because of that, then I can say with a certain level of probability that this random variable is between two quantiles, I should say, from a t-distribution. And because of the symmetry of a t-distribution, you could equivalently write this as negative t, 1 minus alpha divided by 2 with n minus 2 degrees of freedom. You do some algebra, and look what happens. You just get yh nu in the middle, and thus the stuff that's inside that probability, then you can use as your prediction interval. And there's your prediction interval. Where now this y hat, instead of being a random variable, it's now computed from your sample. So it's an observed value. And also, here's this estimated variance as well. And we'll see how this formula for it comes about very, very soon. So there's your interval. And again, it should look very, very similar to what we saw for a confidence interval for the expected value of y, which was right there. Oops. There's the two intervals. Okay. Let's talk more about this variance quantity that's in that interval. Now, as we talked about at the very beginning of class, I said that the interval, the prediction interval, is going to be wider than the confidence interval at the same particular x. And the intuitive reason is because we see those green dots bouncing around the line, meaning having variability in comparison to just a line, which obviously doesn't have any variability at all. Well, where this longer width or wider interval part comes about for a prediction interval comes about right here in the variance. Remember, both intervals use a particular variance in it, and the variance for the prediction interval is larger than the one for the confidence interval. Well, why? Here's why. If you've taken a mathematical statistics class, you learn something like this. Let's see, the variance of A times, I want to write this, the variance of A times, let's say, y1 plus B times y2, where A and B are constants, y1 and y2 are random variables, is equal to A squared times the variance of y1 plus B squared times the variance of y2. Notice I left off one component, the covariance. Those of you who've had a math stat course, when can I leave off that covariance? When I have independence between the random variables. Okay. Let's apply that idea here. The variance of y, h nu, minus y hat h is equal to what I did there. A is basically 1. B is negative 1. Y1 is yh nu. Y2 is y hat h. Well, why don't I have to worry about a covariance here? Well, again, this is where this idea of thinking that after you have your regression model ready, now you want to do a prediction interval for, let's say, a new x that you already have now drawn out of the population, since this is a new observation, then this YH new is going to be independent of the Y hat that you already previously found. So that's why you don't have to worry about a covariance. Okay, so what that means then is that this variance of Y, well, remember how Y is still soon to come about, beta 0 plus beta 1 times now XH nu plus epsilon. And what we have seen before then, when I find the variance of that kind of a quantity, the only thing I have to worry about is the epsilon. That variance is sigma squared. So that's where that comes about. And last time, we actually found the variance of Y hat H. Sigma squared times the quantity that's in the parentheses. So now you can see then the differences between the variance that we had for the confidence interval and the variance for the prediction interval. It's this extra part. So, and unfortunately I removed my split screen here. I guess I did that a little bit too soon. So basically then, in the formula that we're going to use, we have an extra 1 there for that variance part. In comparison to what we use for a confidence. Of course, we will never know what sigma squared is, so what do we do with stuff that we don't know in statistics? Well, we replace that with an estimate. So we replace sigma squared with this corresponding estimate, and that's how you get the estimated variance of YH nu minus Y hat. So that's all there is to it. Any questions? We will come back to this note a little bit later. Let's go to an example. This is on page 225. So let's look at how we can compute confidence intervals and prediction intervals in R. So simply put, let's say we have this. We have a high school GPA of 1.88. I don't know if you actually ever would have that. I think it might be tough to graduate from high school with a high school GPA of 1.88, but let's say that we did, and we want to find a confidence interval for the corresponding Y. I'm sorry, the corresponding expected value of Y, and then a prediction interval for a corresponding value of Y. So let me go over here to R, or 10 first. I'm just going to read in my data as before. And of course use the LM function to estimate my model. I'm going to summarize the fit of that model using summary mod.fit. And as we've seen before, I've done this once before, I'm going to put the results from summary of mod.fit into something called sum.fit so that I can extract some information from it. So there's my estimated information from my estimated model, as we've seen before. And I'm going to pull out, as I've done before, MSE from sum.fit and put that into an object called MSE. So here's MSE. So let's look at how we can use these formulas now to make these corresponding computations. I'm going to actually go back to Word to show you that part and do a split screen. So what I want to do is basically put this formula that we see in the top portion of the screen, put that into the right syntax so that R can actually compute it. First of all, let's say I want 95% interval, so I'm going to set alpha to be 0.05. My sample size is 20 in this particular case. A quick way you can find that is look at the number of rows in your data set using the n row function. As we've seen before, to get a quantile from a t-distribution, you can use the qt function. And I'm interested in a particular value of x of 1.88. Okay, let's go ahead and do that part. Now, as we've done before, let's say if I want to find y hat sub h, what I could do is just simply take b0 plus b1 times x, and I get this back. Notice you see the word intercept above y hat. Anybody know why that happens? or where that comes from. Let's look at mod.fit $coefficients. There you see that intercept. So what ends up happening is R carries forward a label in its calculation, which we don't want, because this is not the intercept. This is y hat. So how can we get around this problem? Now let me just go to the code. Is I use a function called as.numeric, meaning treat this as a numerical value. Don't worry about any labels. So I use as.numeric. I put in my formula for b0 plus b1 times x, then all y dot hat h. Okay? We need some other quantities. For example, notice how we have the sum of the x's minus x bar squared. Some people will often refer to this as SSX, sum of squares for the x's. We could find that. Remember how a sample variance comes about, right? Basically, you take the sum of squares for the x's divided by n minus 1. So I could use the var function to find the variance, take that times n minus 1. To find my x bar that you see in my equation here, I just take the mean of all the high school GPAs. And then lastly, finally, I can actually program in the corresponding formula. So for the lower bound for a prediction interval, here's my y hat, minus the value from the t distribution, times the square root of MSE, times then the quantity, here's my 1, plus 1 over n, plus, and there's that rest of that part there. I'm going to round to 3 decimal places just to make it look nice. That's my lower bound. So notice there's a minus there. For my upper bound, I do a plus. I could do the same thing for the confidence interval itself, but notice here you do not see that 1 as we did with the prediction interval. So let me go ahead and run all this. I'm going to put everything into a nice little data.frame just to print it off nicely. And there's all of our computations. So you can see the actual computations on page 227 as well. Actually put everything into the corresponding formulas. And so we can say with 95% confidence the average college GPA for a high school GPA of 1.88 is somewhere between 1.848 and 2.198. Now, for the prediction interval, we would say with 95% confidence, a student with a 1.88 high school GPA. Notice I say a student. I don't say, not looking at the average college GPA. I'm looking for a student with a high school GPA of 1.88. Their corresponding college GPA is 1.375 to 2.671. You can see how much wider this interval is in comparison to the expected value of y interval. So we have this extra variability that we have to account for. Are there any questions? Now, let's go back to page 224 now and cover that note that I was mentioning before. Now, there may be times where you're not just interested in, let's say, in doing a prediction interval, not just for, let's say, one person's x. Suppose that you have maybe 4 or 5 people with the exact same x, and you want to find a prediction interval now for, let's say, the sample mean college GPA. Well, in that case, then, what you're looking for essentially is this, y bar of h nu, where you're taking the average of m different y's, like maybe 5. The prediction interval is essentially the same except for instead of having a 1 here, now you have 1 over m. Well, of course, if m was 1, look what happens. You get the same thing back that we had originally for the prediction interval. But look what happens when m is very, very big. What happens? What happens to that 1 over m term? It basically is 0. So as m goes to infinity, let's say, that variance, it goes back to the same variance as what we saw for a confidence interval for expected value of y. So remember, we didn't have anything there at all. This was 0 for a confidence interval for the expected value of y. Well, remember what an expected value of y actually represents, basically. And that is, if you were to take an infinite sample size, what would be the mean for y? So you have a nice little relationship here then between prediction interval and the confidence interval. You can see that through that formula. Okay, lastly, for confidence intervals and prediction intervals then. Oftentimes, you don't just want a confidence interval or prediction interval for at just one particular x. Maybe what we like to do is look at all possible confidence intervals and prediction intervals that could occur from the minimum x all the way up to the maximum x. Well, this is a plot of all possible intervals. And we'll talk about how to do the plot shortly. So let's look at the plot first. So we can see here in green, so this is a scatter plot. We have our estimated regression model plotted in red. Unfortunately, it's a little curvy there. It's not supposed to be curvy. It's supposed to be a straight line. And here's my confidence interval, the lower and upper bounds, and here's my prediction interval. So for example, remember we were looking at x equal 1.88, which would be right about there. I project up and then over. And also do the same thing over here. We get what we computed before. The confidence interval for expected value of y is 1.85 to 2.20. Also, the prediction interval is 1.37 all the way up to 2.67. But the nice thing about this plot is that you could do the same thing for, let's say, 2.5. You could do the same thing for 3, 3.5, and so on. So that gives you all the intervals at once. When you see a plot like this, where basically you see these intervals kind of being like a band around that regression line, or the regression model, I should say, these are called confidence interval bands and prediction interval bands. So quite useful. Let's talk about how we actually do one of these plots then. So as we've done before, I'm going to do a scatter plot of my data using the plot function. And then I'm going to use the curve function to actually put then the regression model on the plot. We've talked about using, for example, the segments function. We've talked about using the AB line function. We've also talked about the curve function briefly. Just to review, the curve function, the first argument is EXPR for expression. And this is where I put in B0 plus B1 times X. And you always have to have an X here. Curve allows you to plot functions of one variable, and that variable has to be X. The color of the line is going to be red. Line type is solid. Line width is 1. I'm going to add it to the current plot. And I'm going to draw the line. The code that I have there is fine, but this is the syntax I was using earlier. I'm going to draw the line from the minimum value of X to the maximum value of X. by specifying x_lit. What I have there for from equal and to equal will work too. It's just, I had thought I changed all my notes to be consistent. And unfortunately, I did not change it right there. Make a note to myself to do that. I guess in the notes it's correct. It's just I didn't change my program. Sorry about that. So then I can plot the regression model. So there's a regression model. And now let's plot now the a confidence interval. So essentially what I need to do is just plug in now the equation for the lower bound for the interval. So again, here's y hat as a function of x minus my t-distribution quantity times the square root of MSE times then the rest of that stuff that was in parentheses. Notice how you see x here. So remember that has to vary. And that's going to give me my lower bound for my interval. I can do that also with the upper bound and then also the prediction interval. And there's my plot. One last thing is I need to put a legend on the plot so that you can differentiate, well, which of the lines mean what. Here's a new function we haven't seen before called legend. I'm going to skip this first argument here and come back to it. First of all, the names in the legend, I say legend equal, and I simply use the C function to combine sample model, 95% confidence interval, 95% prediction interval. Notice there's three things in the legend, so I need to have three colors. Red, dark green, blue, corresponding to the colors I use in the curve function. LTY is line type. The regression line was solid, and I failed to mention before that the confidence intervals and prediction intervals are dashed lines. BTY stands for box type. Do I want a box around the legend? No, so I put an N there. And then CX corresponds to how big do I want the legend to be, 75% of the default. So now I'm going to highlight that and run it. And notice we don't see a legend pop up. But when I move my mouse over here to the plot, notice how the mouse changed from that to a plus. The reason being because it's asking me to actually point on the plot with my mouse where I want to add the legend. So if I point right here, the legend drops in. That behavior in R comes about through using the locator 1 argument with the legend. Alternatively, if you wanted to, what you could have done is actually specify x and y coordinates for the legend. So I could have said x equal, let's just say 3, y equal 1. And notice how I had a legend drawn there. Any questions? Some other stuff to see in this plot. Remember how we saw that the confidence interval should always be smaller width than the prediction interval. Obviously, that happens in this plot. But also remember something that we discussed last time. We said that as you get closer and closer and closer to the middle of the axis, or the mean of the axis, we define that as the middle, the interval should get smaller in width. Why? Take a look at the formula again. The reason comes about from this right here. Notice as x is getting farther and farther from x bar, that variance is going to be larger and larger and larger. And you see that demonstrated in this plot. The bands are smaller in width towards the middle of the axis and then wider towards the end of the axis. And again, as an intuitive reason for why that happens is that you know more information about what's happening in the middle than what you know in the end. And the way that we quantify known information in statistics is through variances, essentially. Now the prediction interval, same thing happens for the prediction interval, but it's quite obvious on that plot. But trust me, in the middle there on the plot, towards the mean, the intervals are smaller in width than they are in the end. You can try that on your own, do some calculations to actually see that. Okay. Well, guess what? I showed you the harder way to do these calculations when there's actually an easier way. But it's often useful to know what the harder way is so that you better understand the formulas that we just seen, and also that helps you learn how to use some of the basic aspects of R. So here's a little bit easier way to do some of our calculations, at least for the interval itself. Let's say that instead of just doing one interval for when x is equal to 1.8, suppose I also want it for x equal to 2, 3, and 4, just to make this a little more fun. And so what I'm going to do is create a data frame that has a variable, high school GPA, exactly the same name as what's in my original data set, and it has these 4 different GPAs. I put that into an object called more.gpa. So just to show you that indeed that is true, that this happened. Here's my code. There's more.gpa. Now in a similar manner to what we've used in chapter 1, I'm going to use the predict function here to get y hat, but also to get my confidence intervals and prediction intervals out. So I say predict object equal mod.fit, new data. This is what I want to do my predictions at, or get my y hats for, all the x's in more.gpa. The interval equal confidence says do confidence intervals. Level equal 0.95, that's my confidence level. And lastly, this se.fit equal true is going to give me the square root of the estimated variance of y hat in my output. So let me go ahead and run this. And here we go. So under this $fit part, you see these are my y hats. Here's my confidence interval, just what we computed before. This is on page 230, if you're wondering where we are at. Here's that square root of the estimated variance of y hat. Degrees of freedom, corresponding degrees of freedom that was used in the t-distribution. And lastly, what they also print off here is the square root of MSE. Obviously, that plays a role in the confidence interval, so that's why it ends up being printed off. To do a prediction interval, change interval equal to, quote, prediction, end quote. And there's your prediction intervals, I should say.
Can you bring this together with the axis?
I'm sorry, say it again.
Can you bring this together with the axis?
For these particular axes? Yes. And so what you could do, for example, is suppose we save these results into an object. And I think it's good just to show you how to do this, just for demonstration purposes. So I save them into an object. So for example, save.ci, oops. Well, we just do it for our data here to make this a little bit smaller. So there's, what did I do wrong? Okay, I see what I did. Okay, so there's our output, stored in save.ci, save.pi as well. Oh, I'm sorry, I took some code here. I thought it was doing what I wanted to do to answer your question, but doesn't do it exactly. Why don't we just take a look at this save.ci. Let me make sure I got everything there. Now, if I did name save.ci, similar to what we saw previously when we were doing stuff with the LM function, saving the results, I have a list of items that pop up. So if I say save.ci $fit, so now I just get part of the output that we saw. And what I could do is create a data.frame that has more.gpa in it, and also save.ci $fit in it, and that answers your question. Okay, something I want to mention, this is on page 230, that you need to be careful about, is that when you do the prediction intervals, and you say se.fit equal true, this se.fit here is not the same square root of the estimated variance that you would expect. What it actually is this, the square root of the estimated variance of y hat. But remember, that's not what is used exactly in our formula for prediction interval. Instead, what's used is the estimated variance, square root of the estimated variance of yh minus y hat. So it's not exactly the same as, I should say, not exactly the same. It's not what you would expect. So please be careful about that. Okay. So we've talked about all those notes. Let's talk about how we can do those confidence interval prediction interval plots again. So what I'm going to do is plot my data, put the regression line, plot my data first. And so there's my data, my scatter plot. And then use the curve function to actually plot the regression model. Now before, when we did this, all I did was I put in B0 plus B1 times x. But remember, the predict function gives us the y hats as well. So why don't we just use the predict function? So I'm going to say predict object equal mod.fit, new data equal, and again, this is where you specify what do you want to do the predictions at in terms of the x's. Data.frame, high school.gpa, x. So notice what R is going to do is it's going to plug in a bunch of different values of x, evaluate the model, and then plot it using the curve function. So to emphasize this, let me copy and paste this out of here so we can see what would happen if I had simply, say, 1.88 for x. Notice what I get, a single number, 2.02. Notice you do not see this $fit anymore. You only get that $fit standard error if you were to add those corresponding options. So, if I use the curve function in this manner, there's my line. Well, what about then the confidence interval bands? Again, I can use the predict function. All this is the same as before. Now I'm going to add only the interval and the level argument. Let me copy and paste this out of this and run it as an example to show you what happens. And I get this in return. Notice you do not see that $se.fit or that $df. All you get is what you were seeing previously in that $fit part of the output. And in particular, that second element there is the lower bound for the confidence interval. So if you think of this as a matrix, then notice what I did. Comma 2. So I'll take all rows, the second column, I get my lower bound. So then, when I run this curve function, notice how I have the bracket, comma 2, and bracket there. And when I execute this, I get this on my plot. Okay. So I do the same thing for the upper bound. And for the prediction interval, I do basically exactly the same thing, but now I put prediction in there instead. And also I can put a legend in my plot. Here we go. So there's the plot, just done a different way. And I might be thinking, geez, why are we spending so much time on plotting? Well, we're going to do a lot of plotting in this class, and so it's going to be Very important for you to be comfortable with the curve function. So that's why I take the time to do this.
In this case, it basically you didn't take the formula for the curves. You just took specific numbers and plotted the line for those numbers, right?
When you say I did not use the formula, I'm essentially using the same formula as we did the very first time, but now I get access to the formula using the predict function. Does that answer your question? And it's just a little bit easier. Okay. Let's see here. I'll let you look on your own. Here's some code that can be used to actually illustrate some stuff that I was actually drawing in class that shows that x equal 1.88, there's the bottom bound of the prediction interval. And it's just uses a combination of the segments function, which we saw previously, and also to get that label there, that 1.37, there's a function called M-text that is used. M stands for margin text. Okay. Now lastly, in this section, page 2.33, so one last thing that we need to talk about. So basically what we've done is that, let's say at x equal 1, find a 95% confidence interval. At x equal 1.01, find a 95% confidence interval. At x equal 1.02, find a 95% confidence interval. And we did that through all possible values of x. So we have a whole bunch of 95% confidence intervals. Well, what's the confidence level of the entire band, though? So what's the confidence that I have that all possible expected value y's, let's say, are within the band?
0.
It's not 0.
Very small.
It could be. It probably ends up being very small. Yes, but not necessarily 0. Well, why are we saying that the confidence level is so small? Well, you got to be careful with that statement too, because you're basically assuming independence between each of these. It's not 95%. I'm going to use the word the family confidence level, to use a term that hopefully all of you have heard about in another class. The family confidence level of this band is not 95%. Why? After all, we're using 95% confidence intervals to come up with the band. So if you've taken my Stat 801 class, you should know why.
Multiple comparison.
Oh, basically, this comes down to multiple comparisons. So if you take a Stat 802, but definitely in an 801 course, you do start talking about multiple comparisons. And that is, let's say if you have, let's say, 5 comparisons that you're making of means, each one using 95% confidence intervals. So you're taking like mu1 minus mu2, mu1 minus mu3, find confidence intervals. Let's say there's 5. Each one are 95% confidence intervals. Well, the overall family confidence level is not 95%. And if you could, let's say, assume independence then between each of the different confidence intervals that you're finding, then you can use a binomial argument to find what the actual confidence level is. Anyone here heard of a Bonferroni correction? Hopefully all of you have. That's a common way that people use to correct and to find what the family confidence level is. Could we use a Bonferroni correction here? How many intervals are we finding, essentially? Infinity. That's going to be one big correction there. So there are other ways, though, that you can control the family-wise confidence level so that you know that the band itself has a 95% confidence level. And if you're interested in learning more about that, take a look at the book. Section 2.6 talks about one way. You are not responsible for it, but it is important to point out. Okay. Are there any questions? let's go on to section 2.7. I would like to point out that a lot of the material that we talked about so far is review. Especially if you did actually take Stat 801 here, all the stuff that we talked about so far is stuff that you should have seen in Stat 801. Well, why do we do this? Why do we talk about this stuff again? Well, first of all, some of you did not necessarily have me for 801, so you didn't have the R experience. So this gives you a familiar, the topic, the material is familiar to you. What's new is the R stuff, so you should be spending a lot of time learning how to do the stuff in R. But also, not all of you have taken actually 801, even though that's the prerequisite for the course. You might have taken something similar to 801 someplace else. And depending upon what they've talked about, they may or may not have addressed some of this material here. But starting now, we're going to start do some stuff that's not necessarily taught. At least when I teach Stat 801, it's not necessarily taught in 801. And definitely from Chapter 3 on, that should be all new material for those of you who've taken 801 here. Okay. So what we're going to do in section 2.7 and 2.8 is kind of, the things are different, but there are two different ways of looking at your regression model and to assess, is it worthwhile to use the regression model. And the way that we do that is through partitioning sums of squares. So if you've had any ANOVA experience before, which you should have at least a little bit, you know that ANOVA, analysis of variance, is based upon partitioning sums of squares. So to begin here, suppose that you didn't know what regression analysis was, and you still wanted to somehow come up with a prediction for y. Didn't know anything about it, x at all. Well, what would you use to predict y? Well, how about the sample mean? That seems to make sense. Given no other information, why don't you use the sample mean to predict what the individual y would be? So as a measure then of how good this prediction would be is take all your y's, subtract off the corresponding predicted values, your y bars, square them so that you always have positive quantity, and add them all up. And this is again a measure of how good y bar is as a predictor of y. The specific name is called total sums of squares, abbreviated by our book by SSTO. Other books might use just simply SST, for example. And what this is basically getting at is that a measure of the total variabilities of the y's. You can also think of this as this is the worst you could do in predicting y. Well, now let's remember all your regression experience that you've had over the last few weeks. And we know that if some x out there exists, we could use that x to predict what y is using a regression model and come up with a y hat. How good is that predictor? Well, we've talked about it before. Take all your y's, subtract off the corresponding predicted values, square it, add them all up, and you get the sum of squared errors, or SSE. So now what we have here are two different ways that you can predict y. One not using a regression model, and one using a regression model. How will we compare the two? Well, simply subtract the two sums of squares. So I'm going to take SSTO, which is again the worst you could do, subtract off SSE, so you expect then this quantity to be positive, because you would hope that you're at least going to gain something from using the x's. And so this is what, in terms of the equations, this is what we have. And you could do some algebra and show that this simplifies down to y hat minus y bar squared. Add them all up. This has a specific name, regression sum of squares. Other people might call it sums of squares for regression. We will simply denote it as SSR. Here's a nice little picture then that demonstrates what these different measures are getting at. So this is the college and high school GPA example once again, and I've simply blown up 1 point in my sample. This particular one right there. I've also, in pink there, I plotted the regression model. And also I put a line on the plot for y bar. That again, this is what you would use if you didn't have knowledge of x at all. So a measurement of how good that prediction y bar would be is simply the distance between the blue point and the orange line. Once you use regression, you can see a measurement of how good that prediction is. It's right there, y minus y hat. So what have we gained from doing the regression analysis? Using a regression model? Well, this distance. And essentially what we do then with the sums of squares is we look at all these distances, square them so that they're all positive, and add them up. So, as we saw before, SSTO minus SSE is equal to SSR. I'll just do a little algebra, and that means that SSTO is equal to SSE plus SSR. And you can see that from that plot right there. Now, when you have this part here, you can see how it's broken up into two components. SSTO has n minus 1 degrees of freedom. Well, again, look at the formula for SSTO. It's essentially the numerator in a sample variance. And what do we divide that numerator by? N minus 1, the corresponding degrees of freedom. That's where that degrees of freedom comes from. SSR ends up having 1 degree of freedom. And the nice thing about degrees of freedom in these kinds of situations is that you can simply subtract degrees of freedom from, or take SSTO degrees of freedom minus SSE degrees of freedom, you get SSR degrees of freedom. Another way you can think about this degrees of freedom is corresponds to the number of predictor variables that you have. Right now we're only talking about models with one predictor variable, but starting in chapter 6 we will have more than one. Also, you might want to come up with like an average sum of squares. And we talked about MSE before, mean square for error. Well, that's SSE divided by the corresponding degrees of freedom. MSR, regression mean square, according to our book. That's what it's called, or mean sums of squares due to regression. You take SSR divided by the corresponding degrees of freedom. Well, that's no fun. It's just 1, so you get SSR back. Again, later on we will have cases where the degrees of freedom is different. And then lastly, we can summarize everything into what should be a little bit familiar, an ANOVA table that shows the different parts of variability here associated with our regression analysis. So we have 3 measures of variability. The total sums of squares we started off with, degrees of freedom n minus 1. The sums of squares will be denoted by SSTO. We partition that total sums of squares into 1 for regression and 1 for error. And then we have their corresponding sums of squares and mean squares. And lastly, we have a column denoted by F. And notice what's listed there. F star is equal to MSR divided by MSE. So we're actually going to take a ratio of MSR divided by MSE. And that's going to be something very important coming up. But one way to think about why that's important is to take a look at this plot. Our eventual goal is to determine, is this regression model useful or not? So we've already said that, based upon some other stuff that we've done, it looks like high school GPA is a useful predictor of college GPA. Okay? Well, how is that going to be represented in this particular plot? Well, you're going to have small values for y minus y hat. So if you have, on average, small squared values, MSE is going to be small. Well, what's going to happen then to MSR? Well, if this regression is useful, you're going to have big values of y hat minus y bar squared. And on average, you're going to have big values. So, if the regression model is useful, this number is going to be big. This number is going to be small. What happens to F star? It's going to be big. So if F star is going to be big, that tells you, hey, your regression model is useful. If F star is not big, then you might be worried about, is this regression model useful or not? When would F star not be big? Well, suppose if your regression model looks something like this. You can see how that SSR is going to end up being, kind of small, and your MSE, or SSE too, is going to be kind of big. So that gives you some intuitive explanation for what we're going to be doing shortly. Well, we're going to need to figure out, what's big enough for this F star to say, yes, indeed, that this regression model is useful. And the way that we do that, and is the way that we do this in all our other hypothesis tests, generally speaking, is to compare a test statistic to a critical value or compute a p-value. Well, to do that, we need a probability distribution for a statistic. The probability distribution for F star is going to be an F distribution. F distributions should be reviewed, but just in case they are not, this is what an F distribution looks like. Kind of a messy looking equation there. I expect you to be able to write out this equation on a test. Just kidding. It's kind of messy. What you need to know is, how can I find quantiles? Notice that in blue. I have percentiles. Essentially the same thing. I want to be consistent, use quantiles. How to find quantiles, and also how to find probabilities associated with this F distribution. So if Z has an F distribution, what we might be interested in doing is this. Find a particular value from the distribution such that the probability to the left of it is 1 minus alpha. We just symbolically denote this particular quantity as F sub 1 minus alpha, and there are two parameters in this distribution that we have to worry about. What's often referred to as a numerator degrees of freedom and a denominator degrees of freedom. They control the shape of the distribution. So, for example, this is taken from when I've taught Stat 380, and also I use this in Stat 801 as well. What I have is a little plot here showing a F distribution. This is drawn to scale, where the numerator degrees of freedom is 5 and the denominator degrees of freedom is 20. And in pink here, this line here represents 2.16. So the area to the left of it is 0.9, and the area to the right of it is 0.1. So we say that the 0.9 quantile from an F distribution with 5 numerator degrees of freedom, 20 denominator degrees of freedom, is 2.16. Notice that this distribution is right-skewed. It will always be right-skewed. And we can see as the area to the left of our number of interest, or quantile of interest, gets big, we can see then that the quantile gets big. So for example, it's hard to see here, but it's right here, 6.46. If you want to see the corresponding Excel file, there it is from my Stat 380 website. When we do this stuff in R, it's fairly easy. There is a function R called QF, quantile F distribution. I want the 0.9 quantile, so I use that for my probability argument, just like what we did with the T distribution. DF1 is the numerator degrees of freedom. DF2 is the denominator degrees of freedom. And so then the probability that Z is less than 2.16 is equal to 0.9. To find probabilities, use the PF function. Okay. So we're going to use this F distribution then to do what's often referred to as an F-test. An F-test allows you to determine, is beta 1 equal to 0 or versus beta 1 does not equal 0. Well, hopefully those hypotheses sound familiar. We've actually done this before using a t-distribution. Again, there's our regression model. If beta 1 is equal to 0, obviously x is not helpful to predict y, expected value 1. If beta 1 does not equal 0, then that says, yeah, this model seems to be useful. Now to do this test, just like what we did before, now instead of using the t-distribution and a particular statistic that we looked at, I'm going to use this F statistic, called F star. And I've given you some intuitive reasoning for why this F star tells us if our model is useful or not. Here's a little bit more mathematical justification. One can show, you're not responsible for this, but one can show that the expected value of this MSR is sigma squared plus this quantity here, and notice beta 1 is in there. Well, if beta 1 is equal to 0, what happens to the expected value of MSR? It's just simply sigma squared. Okay? Also, expected value of MSC always, no matter what beta 1 is, always will be sigma squared. Mathematically proven. So look what happens then when you take the ratio of the expected value of MSR divided by expected value of MSE. If beta 1 was equal to 0, what's that ratio going to be? 1. If beta 1 does not equal 0, what's that ratio going to be? Something greater than 1. Okay? Well, will we ever know what the expected value of MSR is and the expected value of MSE is? No. So let's just replace them with their estimates and look at some quantity we call F star. And we look for big values of F star to say, yes, indeed, beta 1 does not equal 0. Values of F star close to 1 suggests maybe beta 1 is 0. Well, to make then that judgment then, that's where the F distribution comes in. So we know that F star, if the null hypothesis is true, we know that F star has an F distribution to it. And so what we can do is go to a critical value, 1 minus alpha quantile from the F distribution to make this judgment. Notice the numerator degrees of freedom is 1. Well, what's in the numerator of F star? MSR. Remember that had 1 degree of freedom. Denominator degrees of freedom, n minus 2. Well, what was in the denominator? MSE. So step 4 of a hypothesis test, then we decide to reject or don't reject HO. And so this is what it looks like. This is actually a one-sided test there because we're working with actually squared quantities. And anything to the left of your critical value corresponds to don't reject HO, meaning that if my F star is here, I don't reject. Anything to the right says that my F star is large, and I end up rejecting HO. Then step 5, your conclusion. Well, then you tell me what reject HO and don't reject HO mean in terms of the problem. Just like what we did before. What about a p-value approach? Well, now instead of looking at the location of F star with respect to the critical value, now you look at areas underneath the curve. That's what we do with p-values. So if F was a random variable, then our p-value would be the probability that F is greater than F star. Step 3, state alpha. Step 4, you reject if the p-value is less than alpha. Don't reject if p-value is greater than alpha. And that takes us to an example, and unfortunately it also means that we are out of time as well here. So you have enough background now in order to do the project. Once we got done with the prediction intervals and confidence intervals, we covered everything that you need to know with the project. If you have any questions about the project between now and Tuesday when it's due, please feel free to post a message to the listserv. I'll be checking my email over the weekend, so I don't mind answering questions that pop up. Are there any questions, though, at this time? Okay, that's it for today.